Hello, Miss Lahart here for LT2 of the chapter on probability. So since the basic calculations within probability involve counting the number of outcomes that fit into a particular event, it makes sense to have a tool to visualize and keep track of all the outcomes in a sample space. We will do this by using sets. Recall the basic definition of a set. A set is a simple collection of things, numbers, objects, etc., that satisfy a well-defined criteria. The things that are contained in the sets are called the elements of the set. So for example, the set A is defined as the collection of all integers that are greater than 0 and less than 10. So if we were to list them out in roster form, it would look like this. Okay, and it's set A. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Show set A in a Venn diagram. It'll be very simple because there's only one set. So here's bubble, and all the numbers are in it. Okay. A subset is any set that the elements are all contained within another set. So give two possible rules that could define subsets of A, and then write the sets as B and C in roster form. Do sets B and C have any elements in common? Okay, so looking at my numbers, let's go even numbers. Okay, so if I'm talking about even numbers, B would be 2, 4, 6, 8. Okay, let's set odd numbers for C. So we got 1, 3, 5, 7, 9. And then the question, do they have anything in common? No, they don't. So you can either do an empty set like that or the null set, which looks like that. Okay. Both those mean they don't have anything in common. There's no numbers in both of them. Let's go back to a probability. So consider an experiment where we first toss a coin and then note the outcome and then roll a six-sided die and note the outcome. Write a set of ordered pairs, such as H4, that represents all outcomes for this experiment. Recall that this is called your sample space. We generally call this set S. So, and please feel free to pause the video. You have to write them in ordered pairs. So, well, I can flip heads and then I can get one of 6 of the numbers. So H1, H2, H3, H4, H5, H6. Or I can get tails and also get 1 through 6. So there's my sample space, all of those things. Write a set of ordered pairs that represents the event of getting a tail and an even number. Call this set A. So tail and an even number would require T2, T4, T6. We only have 3 choices for that. The complement of set A will be all of the events in the sample space S that do not fall in A. So the opposite of A is everything else. Write out the complement of set A. We'll call this set B. So set B would look like this, getting rid of T2, T4, T6. All the H terms will there. And then we have T1, T3, and whoops. That's a mistake. T5, right there. Off to a great start. Got to remember to fix that. Okay. All right. Probability of set A. So I have 1, 2, 3 out of 1, 2, 3, 4, 5, 6, 12. So I have 3 out of 12. And again, number in set A, number in S. That would be 3 out of 12, which is 1/4. Okay. Probability of B. Well, how many do I have in this set? We have 6, 7, 8, 9. So 9 out of 12, which reduces to 3/4. Basic probability with all this beautiful numbering sense, function notation. Again, number in A, number in set. A set and its complement are important in probability because all outcomes either fall into an event or its complement, but not both. Called mutually exclusive. We'll get into that later. Different textbooks use different notation to denote the complements. Since notation is not universal, we simply refer to complements by name instead of by symbol. Consider rolling a single 6-sided die and recording the results. Let set A be the event of rolling a number greater than 4, and let set B be the complement of set A. So draw a Venn diagram that illustrates the sample space S and sets A and B. Okay, so here is my box. The box is all possibilities. I have set A, I have set B. Because B numbers being greater than 4, we're only going to have 5 and 6. And then in B, we're going to have everybody else. What's the probability of picking something in A? Well, we have 2 out of the total 6. So that's 1/3. And then in B, we have 4 out of 6. which is 2/3. Okay. Now, what is true about the sum of the probability of A and the probability of B? So if I add 1/3 and 2/3, I get 3/3, which is a whole. 1 or 100%. Okay. Prove that the sum of the probability of an event will be the probability of its complement will always be 1. I'm going to move to the next slide just to kind of get the work down. Pause the video if you need to write any of that down. So proving it, we're going to prove that if you add, it equals 1. So how do we prove that? Well, the number in A and the number of S plus the number of not A and not S. But think about it, guys. You're going to take the set of numbers and subtract what's in A. So if you think about it, what's going to happen? We both have common denominators. So we end up with this situation. The n of A ends up canceling, leaving us with n of S over n of S, which is equivalent to 1. And therefore, I have just proved that the set and its complement will always be equal to 1. Always. Okay. We use the relationship developed in D all the time without even thinking about it. Try the following examples. Answer the following problems by using the relationship developed in exercise 3 of D. So, if the probability I'll draw a red marble from a bag of 3/17, what's the probability that I won't do it? Well, if I take the probability of red plus the probability of not red, switch it around. If I want just the probability of not red, I take 1 minus probability of red. So 1 minus 3/17 is 14/17. Okay. The probability that it will rain tomorrow is 20%. What's the probability it won't rain tomorrow? Don't overthink this, guys. Take 100% minus 20%, you get 80%. You're just subtracting the complement away. If you know one, you can know the antonym or the other part. Good stuff. Theoretical probability calculation, the set that makes up a sample space, can get difficult to write out. It's good to remember things like tree diagrams to help. 2 4-sided die are rolled, and the number on each is noted. Draw a tree diagram that represents it. So in the first row, I got 4 probabilities, right? 4 choices. 1, 2, 3, 4. In the next outspace, I have 4 choices from that. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. How many are there? Well, how many do we have in this last? We got 4, 8, 12, 16. So we got 16 outcomes. I don't know why that's not popping up. 16. Okay, moving on. What is the probability that you don't get 2 of the same number? You don't get. Okay, well, let's use that. We don't get 2 of the same number. Let's figure out how many ways to get 2 and then subtract it away. Okay, so 1, 2, 3, 4 of those choices have 2's in them. 4 of those choices have 2. Wait. Yes. So 1 minus 4 out of 6 equals 12/16, which is 3/4 or 75%. 2 2's. Okay. Oh, you don't get 2 of the same number. Oh my goodness. Step 1, always read it. Just confused myself, everybody. So therefore, I have 1 1, 2 2, 3 3, 4 4. That is 4 out of 16. So 1 minus 4 out of 16 is 12 out of 16, which is 3/4 or 75%. Woo! Missed the heart out. That video hopefully went well. Hopefully you can do the classwork.